Hi guys, let's take a look at what I think you will feel is a relatively quick and easy section here with 7.7. And unfortunately, with using the Achieve system, I really can't see if you're doing the actual proper integration. But I will be sure in this video to show you what the proper integral would be in each of these scenarios. So section 7.7 is all about improper integrands. So most of the problems will consist of limits of integration in which the function on the inside would be defined at, whether that's an infinite limit of integration or a negative infinite limit of integration, such as in number 1 and 2, or like, for example, in number 3, where you're trying to have a limit of integration in which the function would be undefined at. And in all of those scenarios, it's going to be okay because we understand that what that integral is representing is the area between the two values. It's really irrelevant whether it exists or not at an endpoint. It's just relevant that it exists at the points in between. Okay, so let's go ahead and look at the first problem here, where it's asking us to integrate from 1 to infinity of dx over x to the 17/18th power. So the problem with this is that you have a limit of integration at infinity. You can't evaluate any function at infinity and get a real value. So we say, well, all right, then let's take the limit. And for any time it's an upper limit, I'll always use b. For any lower limit, I'll always use a, because the limit is usually defined as the limit from a to b. So in this case, I'm going to say let's let the limit as b approaches infinity of the integral from 1 to b. You'll see I rewrote the inside as just x to the negative 17/18 power, which makes it more easy to use the power rule in the next step. I do that, and I can say, well, this is going to be the limit as b approaches infinity of this x to the negative 17/18. You would add 1 to the exponent, which makes it x to the 1/18th. We know then you would divide by that new exponent, which I did by multiplying by 18. So now we're trying to take the limit as b approaches infinity of this expression, evaluated from 1 to b. Well, I already know when I plug in b, it's going to be a number approaching infinity, and a number approaching infinity to any power is still infinite. Now, I went ahead and showed that over here by just showing, well, it's an infinite number. And then minus your lower limit, when you plug a 1 in, you would get 18 times 1, which is 18. Well, clearly, any infinite number minus a finite number is still an infinite number. So you'll see here in number 1, I put infinity in as my answer, and Achieve liked it. Now, sadly, I didn't have to do any of that formal notation. I could have just understood the answer was infinity, and Achieve would have been fine with it. I wish they would require you to show some steps of your work. In this number 2, the indefinite integral from negative infinity to 4 of this exponential function. Well, again, I need to clear up the improper integral and make it a proper integral. I do that by saying, let's take the limit as a approaches negative infinity of the integral from a to 4. Now, and in this step, I needed a dx that's still being integrated, or sorry, a dt that's still being integrated. So I'll squeeze that in. And then we can say, well, we need to integrate that exponential function with respect to t. We know the integral of any exponential function is that exponential function divided by the derivative of its linear exponent. This is still inside of a limit as a approaches negative infinity, evaluated from a to 4. Now, when I plugged the 4 into this function, I got e to the 0.002 power. 4 times 5 is 20, which moves that over one place. So I get e to the 0.002 power divided by 0.0005. And now you would say minus the lower limit. Well, that lower limit, a is going to be replaced with a negative infinity, so you're putting a negative infinity there. That's going to force that e down to the denominator, and e to the infinite power in the denominator is going to make that fraction go to 0. That's why you see a 0 there. Now, in order to simplify this, and I'm sure I could have put it in that format, but I just said if I'm dividing by 0.0005, that's the same thing as multiplying by 2,000. So I have 2,000 e to the 0.002 power there. Let's see if I can make that a little bit more clear. Yeah, that's a little better. All right, so now I go back to achieve, put that answer in, and you can see again, they liked it. The next one here. We have the integral from 0 to 13. As I mentioned at the beginning of the video, this function does not exist at 13. You have 1 over 0, which is undefined. But I show that that doesn't matter by making this a proper integral, and I can say, and keep in mind here, in problem 1 and 2, I didn't need a one-sided limit, because if you're approaching infinity, obviously you're approaching infinity from numbers below infinity. If you're approaching negative infinity, obviously you're approaching from numbers above negative infinity. But in this case, in order to make this a proper integral, you really need the one-sided limit. You can't just say the limit as b approaches 13, because that would mean b could approach a 13 from numbers above 13 or numbers below 13. We are specifically only approaching 13 from below, so we must show that. The limit as b approaches 13 from the left, from 0 to b. I went ahead and simplified this to 13 minus x to the negative 1/2. Then I use my power rule. Now remember, whenever you integrate a linear function to a power like this, you'll say, well, I'll increase the power by 1, which makes this go to a positive 1/2. I would divide by that power, which means multiply by 2. But then you also divide by the derivative of the inside, which divide by negative 1. That's where the negative 2 came from. So this is the integral of that function. Now I need to evaluate this from 0 to b as b is approaching 13. Well, if I allow b to go to 13 and I plug that in, that's just going to be negative 2 times 0. I get a 0 for the upper limit. Now I would subtract the lower limit, but the lower limit is negative. That's going to make it plus 2. And then 13 minus 0, that's just going to be 13. And we can say, well, that's to the 1/2 power. I'd prefer to write that as 2 on the root of 13. Final answer. And again, you can see that's the same thing I inputted to achieve. For number 4 here, we have the integral from 3 to infinity. Again, one of our limits of integration is not a real number when we try to plug it in. So we say, well, our function is undefined at infinity. So I'll have to say the limit as b approaches infinity is going to take the place of that upper limit. Now, when I use the power rule to integrate, pretty straightforward here, x to the negative 3rd over negative 3. I went ahead and simplified that to negative 1 over 3x cubed. That just looks better. And now you're evaluating this from 3 up to b, where b is approaching infinity. If you evaluate your upper limit, clearly if you plug an infinite number in that denominator, that fraction is going to 0. Now, you would subtract your lower limiting amount when you plug it in. So you'll have minus a negative 1, which becomes plus 1, and then you'll have 3 times 3 cubed. That's 1 over 81. You get your plus 1 over 81. For number 5 here. Now, if you're thinking, hey, these problems are quite a bit shorter than the ones in previous sections, they are, sadly. This section is just not as much fun. For number 5, we have the integral from negative 3 to infinity. Again, I have a linear function to a power. This is similar to number 3. The thing that distinguishes it from number 3 is that it's not undefined at a particular value of x other than you can't take it towards infinity, whereas number 3 was undefined when x is 13. So for number 5, I just need to replace the upper limit with the limit as b approaches infinity, and I'll put a b in that place. And I could have went ahead and put x plus 4 to the negative 3 over 2 power here. And then when I would have integrated it, it would have been x plus 4 to the negative 1/2 power divided by negative 1/2. Well, if you divide by negative 1/2, you multiply by negative 2. And x plus 4 to the negative 1/2 means that you're going to have an x plus 4 inside of a square root in the denominator. So this is my integrated answer here. And then I can say, well, now let's evaluate this from -3 to b as b goes to infinity. Allow b to go to infinity, you're going to have -2 over the square root of an infinite number goes to 0. Minus the lower limit becomes plus, because minus a negative, you'll have 2 over -3 plus 4. Well, that's going to be 1 inside of that square root. 2 over the square root of 1, we just get our 2. And you can see that that's the same answer on Achieve for this one. For number 6, we have the integral of 6 to infinity of e to the -4x. These are pretty quick and easy. You can just say, well, again, I'll have to replace the upper limit with a b as b approaches infinity. The integral of any exponential function is that exponential function divided by the derivative of its linear exponent. So I divide by -4, same thing as multiplying by -1/4. Now, when you're evaluating this, when you plug in that number approaching infinity, you're going to have e to the negative infinite power. That means you're going to have e to the infinity in the denominator. 1 divided by 4 times infinity goes to 0. Now, your second term from your lower limit, you'd say, well, subtract the lower limit, minus a -1/4 becomes plus 1/4, and then you'll have e to the -24th. You got your positive 1/4 e to the -24th. Final answer there. For number 7 here, the lower limit cannot be negative infinity. You can't plug that in and get a real number. So we say, well, then we can take the limit as a approaches negative infinity of the integral from a to 0 of e to the 11x. And then similar to the problem preceding it, you can just say, well, this is going to be e to the 11x divided by 11, or 1/11th e to the 11x. Now when you evaluate at your limits of integration, think about what happens when you plug the 0 in. E to the 0 power is 1. You'd have 1/11th times 1. You got your 1/11th there. Now, your lower limit, you would have e to the 11 times a negative infinity. So that's e to the negative infinity, which means that exponential function would belong in the denominator. You're going to have 1 over 11 times an infinite number. That goes to 0. So your lower limit is 0. Your only answer is your upper limit. You got your 1/11th. For number 8 here, finally, we had to do some techniques of substitution in these problems. For number 8, I had the integral from 0 to infinity of x to the 8th over 2 plus x to the 9th squared. So I said, well, all right, I'll go ahead and create a proper integral. Just say it'll be the limit as b approaches infinity, the integral from 0 to b. Then I looked at that denominator, 2 plus x to the 9th, and I can say, well, if I let what's inside of that group being squared, the 2 plus x to the 9th, equal u, then du would be 9x to the 8th dx. So I knew that that x to the 8th and the dx could cancel out and become du as long as I multiplied a 9 on the inside with it. So in red, I showed I'll multiply by 9 on the inside, divide by 9 on the outside. Now on the inside, the 9x to the 8th dx all becomes du in this step. And then your group to the second power in the denominator just becomes u to the -2. You know how to integrate that. You can just say, well, power rule would become u to the -1 over -1. And then that looks sloppy. Plus, another thing here, I did not want to change my limits of integration to terms of u. So please notice here, instead of changing my limits of integration, which I would have to do if I wanted to keep it in terms of u, I would rather put it back in terms of x and evaluate from x equals 0 to x equals b. So I showed that here. Now, if you just put 0 and b, that would be improper notation because that would assume u is ranging from 0 to b. It's not. So I went x equals 0 to x equals b. Same thing in the next step. When what's inside is in terms of u, I show my limits of evaluation are still in terms of x. Now I go in and I can say, well, this is going to simplify to be -1 over 9u, which becomes -1 over 9 times the group u is equal to, the 2 plus x to the 9th. Now that that's back in terms of x, I don't need to put that x equals 0 to x equals b. It's implied to be x equals 0 to x equals b. So now when I evaluate from 0 to b, you plug in the b, your denominator is going to go to infinity. That means your fraction goes to 0. You plug in the 0 for the lower limit, you're going to get minus a -1 plus 1 over 9 times 2. We get our 1/18 for that final answer there. Next question. For number 9 here in this section, again, not a whole lot of work to this one. What I did on this one, though, is I had to use one of the table integral formulas to simplify this expression. We have the integral from 0 to 2 of dx over the square root of 4 minus x squared. Now, this isn't like some of the earlier problems that I just said, hey, it's just a linear function to a power. It's more difficult to integrate when the inside term is a quadratic, and I don't have an x term in the numerator to use substitution like I did in the last problem. Instantly, I recognize, hey, I could use, since it's a squared minus x squared, I could let x equal 2 sine theta, and this problem would work out wonderfully. I just took a shortcut here and I used a table integration formula, but you could have used the trig substitution and that would have been gorgeous. The goal of this section, though, was just to create a proper integral and then integrate in the most efficient manner possible. So that's what I did. So I integrated from 0 to 2 by saying this function does not exist at 2. So I have to take it the limit as b approaches 2 from the left of the integral 0 to b. Now, when I integrate what's inside of that, I used number 15 from the table of integrals, and let me show that here. You'll see my integration table here. Number 15 says the integral of du over the square root of a squared minus u squared. It's simply the inverse sine of u over a plus c. So you just say whatever that number is, you take the square root of it and put it in the denominator of your inverse sine function. Pretty simplistic. So now, when I go back to my work here, that's exactly what I did. I just said, well, this is going to be the inverse sine of x over the square root of 4, which is 2. I don't need the plus c part because this is a definite integral. This is going to be evaluated from 0 to b as b goes to -2. Sorry, 2 to the left. So now, when I plug in that value of b, which is approaching 2 from the left, that's the inverse sine of 2 over 2. Just gives me the inverse sine of 1. My lower limit's going to be the inverse sine of 0. I know the sine function is 1 at pi over 2, and I know the sine function is 0 at an angle of 0. So inverse sine of 1 is pi over 2, inverse sine of 0 is 0. I just get my answer of pi over 2 here. Piece of cake. For number 10, as soon as you see a natural log in there, you should have been thinking, ooh, this problem's going to require integration by parts. So whenever I first did this problem here for number 10, the actual workflow of the problem is not really what you see. You think I went from here to here. I did not. I wrote down the problem and I instantly came down here and I said, let's not worry about that definite integral just yet. Let's figure out what the integral of the natural log of 10x dx is first and foremost. Then we can go back and worry about making it a proper integral and evaluating at the limits of integration. So I did this work first. I came down here and said, okay, natural log, I'm going to let that be the u, and then everything else, which is just the dx, has to be dv. We differentiate u. Derivative of any natural log is the derivative of what's inside the natural log, 10, divided by what's inside the natural log, which is 10x. You can see this just simplifies to 1 over x with respect to x. The integral of 1 with respect to x is x. So now integration by parts formula says u times v, x, natural log of 10x, minus the integral of v du. That would just be the integral of 1 with respect to x. We already know the integral of 1 with respect to x is simply x. So the integral of the natural log of 10x dx would be x natural log of 10x minus x plus the constant of integration. Now, that constant of integration, of course, is irrelevant when we come up here to our definite integral. First thing I wanted to do in the definite integral was to create a proper integral. And I'd say, well, I know logarithmic functions cannot exist at 0. So I cannot include that 0 as a limit of integration if I want to have a proper limit of integration. So I said, well, okay, we're approaching 0 from numbers above 0. The limit as a approaches 0 from the right, the integral from a to 1 from the natural log of 10x with respect to x. I went ahead and showed what the inside integrated to, and now I'll evaluate from a to 1. When you plug in the 1, we know that you're going to have your 1 times the natural log of 10, then you have minus 1, so that's my upper limit. Your lower limit, well, when you plug in the 0, 0 times anything is 0, so 0 times natural log of 0, that's just going to be 0, and then you have minus 0 when you plug the number approaching 0 in for x. So your whole lower limit simply 0. So you're going to get natural log of 10 minus 1, which is simply your upper limit, evaluated for your answer there. Pretty nice problem. Now, a lot of the remaining problems here are just going back to what I talked about in the notes, where we have, I said the integral of 1 over x to the p. And let me refer to something I put here at the end of this right here. If you're inside of an infinite integral where numbers are going off to infinity, or even if it's going from negative infinity to some finite value, if the degree of the denominator and whatever your expression is can always reduce down to something like this. If the degree of the denominator is more than 1 greater than the numerator, it's going to converge. If the degree of the denominator is not more than 1 greater than the numerator, it's not going to converge, and it's just going to diverge off to infinity. It's because the fraction doesn't get small enough quick enough to converge to some value. Now, we showed this in the notes whenever I integrated something like 1 over x. You know, 1 over x integrates to the natural log of x. Whenever you try to evaluate the natural log of x at an infinite limit of integration, it goes off to infinity. That's why whenever the denominator is just 1 greater than the numerator, it diverges, because you're going to end up with a natural log of infinity. If you have a square root or something down in the denominator and you integrate that, that power is going to go up to the numerator, because x to the negative 1/2 power integrates to x to the positive 1/2. And then you'll be evaluating infinity to the 1/2 power, which is infinity. It would still diverge. You have to have that power be greater than 1 in order for the variable to stay in the denominator. Something like a 1 over x squared. We know that that's going to integrate to be x to the negative 1 divided by negative 1, so negative 1 over x. You evaluate that at infinity, your number is going to 0. It will converge. That's why it always converges anytime the degree of the denominator is more than 1 greater than the degree of the numerator. So now I backtrack to what we're looking at, number 11, and what I'm wanting you to see here, and it's as simple as this. It really is. The degree of the denominator is only 1 more than the degree of the numerator. So this is essentially just like the integral of 1 over x, where you say, well, 1 over x would integrate to be the natural log of x. When you try to evaluate the natural log of x at infinity, you get infinity. Thus, it diverges. This will diverge for the exact same reason. So do I need to worry about what the integral of that is? No, you could, but there is no need to. So what I'm wanting you to see here is that this diverges to infinity. In order to be convergent, a denominator's degree needs to be more than 1, or 1 more than the numerator's degree. More than 1 more. Oh, sorry, that's not worded very well. Needs to be more than 1 more. I should have said greater than 1 more than the numerator's degree. For example, here, I tried to show what iteration of this problem would make it converge. Well, okay, what if I change that denominator from 1 plus x to the 6th to 1 plus x to the 7th? Now the degree of the denominator is 2 more than the numerator. Guarantee you, it's going to converge. However, this problem will not converge. It diverges to infinity. Now, Could you actually integrate that one out by the substitution method and say, well, what if I let u equal 1 plus x to the 6th and du equals 6x to the 5th? Sure, you could do that. I promise you, though, you're going to get an answer that goes to infinity, because every single solitary time, if the denominator's degree is only one more than the numerator, and you have an infinity or a negative infinity as a limit of integration, it's diverging, because your answer is going to involve natural logs. For number 12, we have the integral from negative infinity to infinity of x cubed e to the negative x to the 4th. Now, what I did, I just thought about this function. You have an odd function times an even function. Anytime you have an odd function times an even function, you get an odd function. So if you think about the way that the graph of this is, it's going to be symmetric with respect to the origin. So as soon as I knew that, I just said, well, if I'm integrating from the exact same number to the exact same number, those are going to cancel each other out and total 0. Period, end of story. So it's just like if I would ask you the integral from negative 10 to 10 of x cubed. You say, well, the area from negative 10 to 0 is going to counteract the area, because it's going to be equal and opposite to the area from 0 to 10. For the exact same reason that would give you an integral of 0, this one does as well. When I look at my next problem, it's the exact same thing. 7 divided by the cube root of x, that is an odd function. Any single odd function evaluated from negative a to a, in this case negative 1 to 1, it's going to have an integral solution of 0. So those are pretty straightforward, just because they're using your odd integral powers from negative a to a formulas that we talked about in earlier sections. Now for the next problem here, number 14. Let's see, and I'll go to it right here. We have the integral from negative infinity to infinity of dx over 4 plus 25x to the 2nd. Now, as soon as I saw this, I knew it was going to converge, because you have limits of integration infinity, sure, but your denominator is 2 degrees greater than the numerator. This one should have an answer. So I went in and I worked it out. I can say, okay, first thing I did is I looked at the function on the inside. This time, the function on the inside is an even function. You have 1 over 4 plus 25x squared. All of those terms are even. This is an even function, which means it's symmetric with respect to the y-axis. That enables me to just say, well, then the integral from negative infinity to infinity is 2 times the integral from 0 to infinity of this. Now, this is just me trying to make it a proper integral. So I can say, well, instead of having infinity as a limit of integration, I'll take the limit as b approaches infinity and put a b up there. Now, whenever I started trying to simplify this out, what I did is I said, well, okay, what I can do is I can factor out a 25. And when I do that, this front is really going to be a coefficient of 2 25ths. I showed it as 2 times 1 25th here because I did it in 2 steps. But if I factor a 25 out of that denominator, this first term becomes 4 25ths, and the second term just becomes x squared. Now, dx over 4 25ths plus x squared, I can say, well, that's your formula. 1 over a squared plus x squared is equal to 1 over a inverse tangent of x over a. Gorgeous. Number 16 on your table of integrals. It's one that you really should be using so much that you have memorized. I have it memorized, ingrained in my mind. So a in this case, or a squared I should say, is 4 over 25. So 1 over a would be 1 over the square root of this number. Square root of this number would be 2/5. 1 over that gives me the 5 over 2. And then the x over a becomes x divided by 2/5, or 5x over 2. So same thing there is there. The coefficient of the inverse tangent becomes what's multiplying the x on the inside. And now you say, well, okay, this can be simplified. I can say this 5 over 2 is going to multiply the 2 25ths to give me 1/5. I'll have the limit as b approaches infinity of 1/5, the inverse tangent of 5x over 2. Now we're evaluating at our limits of integration from 0 to b as b goes to infinity. First thing you have, well, if you plug that b in, you've got the inverse tangent of an infinite number. I tried to show my thinking over here by graphing out the inverse tangent graph. You remember the inverse tangent graph is generated from just the graph of the tangent function from negative pi over 2 to pi over 2. You might remember the tangent function looks like the graph of kind of like y equals x cubed stretched between vertical asymptotes at negative pi over 2 to pi over 2. Well, it's no coincidence that the inverse tangent kind of looks like the graph of the cube root of x. However, unlike the cube root that has a infinite range, this function does not. Instead of vertical asymptotes at negative pi over 2 and pi over 2 like the tangent function has, it has horizontal asymptotes. The lowest it can ever go is negative pi over 2, and it can only approach that. Same thing on the top end. As x goes to infinity, the y value will approach pi over 2. So this is saying, well, what happens as the inverse tangent function goes to infinity? Well, the limiting value is pi over 2. That's where this comes from. So I have 1/5 times the upper limit, pi over 2, minus the inverse tangent of 0. Well, when you go to 0, your inverse tangent function goes to 0. So the inverse tangent of 0 is 0. You get 1/5 times pi over 2 for your pi over 10. And hopefully you're thinking, that's pretty cool. It is. The next one is, again, one of those quick problems I'm just wanting you to think about. There's really not any work involved. It's the integral from 4 to infinity of 1 over the 7th root of x cubed minus 9. Okay, so whenever it's saying use the comparison test, it's wanting you to think about the power of p that this is equal to. You say, okay, what am I supposed to remember? I'm supposed to remember that if I have something like 1 over x to the p, how is that going to converge? Only if that denominator has a power greater than 1 more than whatever the numerator's power is. Well, and it's going to diverge if that denominator is of power less than or equal to 1 more than the numerator. Okay. So I go back up here and I say, well, okay, that denominator, it's really x to the 3/7 power. What do I know about that? Well, x to the 3/7 power is less than or equal to 1. What do you know anytime the denominator is only 3 over 7 powers greater than the numerator? That tells you that that fraction is not getting small enough, fast enough to get any convergent answer. It's going to diverge. So it's a simple matter of, hey, anytime p is less than or equal to 1, diverges. Period. End of story. Now, for my next problem here, I go in and I can say, well, all right, for 16, similar problem. It's giving me, now, in this one, it asked me, instead of just using the comparison test, unlike the last one where I didn't have to use it, it physically said, please use it in this one. Use the comparison test to tell whether the integral converges. And of course, you don't have to do this, but I wanted to this time. So it's really the same logic as the last one. You could look at it and just say, John, the denominator is p to the 1/2 power. It's x to the 1/2. Numerator is 1. The difference is 1/2. Therefore, this problem is going to diverge. End of story. It really is. But if you're wanting to use the logic of what they say the comparison test is, technically, this is not a p-series. A p-series is when you just have 1 over x to the p, like this right here. This is 1 over x to the 1/2. Now, that is a divergent integral since p is equal to 1/2, and that's less than or equal to 1. The logic is, again, this denominator is not going to get large enough, quick enough to make that fraction small. So you're always going to be adding fairly large numbers, and the sum of infinitely many fairly large numbers goes off to infinity and diverges. Okay, now the logic in how we simplify our problem is you say, well, okay, our denominator, since we're subtracting 2 from it, it's always going to be less than this denominator. What do you know about two fractions that have the same denominator but different denominators? sorry, same numerator, but different denominators. You can say, well, the fraction with the smaller denominator has to be larger. That's all I'm saying here. Since this denominator is less than this denominator, the fraction in our problem has to be larger than the fraction in this problem. Now, what do we know about this fraction? Well, this fraction is a integral of a p series with p equals 1/2. Thus, it diverges. That means it goes off to infinity. So if that goes off to infinity, and I have conclusively shown that this fraction has to be larger than that one, then our function also, or the integral of our function also must diverge or go off to infinity. So gorgeous problem there. We say for 16, it clearly diverges because it's going to go off to infinity even more quickly than the function 1 over the square root of x, which diverges. For number 17 here, the last question, we have the integral from 8 to infinity of 1 over x squared natural log of x. As soon as I see this problem, I'm just looking at it and saying, well, the denominator is more than 2 more than the numerator. This is going to have a convergent answer, period. Now, so I could already say it's the first choice, move on, but trying to show the comparison test. So again, the comparison test would have me think about this. They want me to understand, hey, I could integrate 1 over x to the second all day, and it would integrate to -1 over x, and then I could evaluate that at infinity, and it gives me a 0. It's going to be 0 minus a -1 over 8 whenever I evaluate. And you say, oh, well, then the integral of 1 over x squared dx, it's just equal to 1 over 8, period. That's a nice convergent answer. And you say, well, why don't you just go ahead and do that for this one? Because I can't integrate that. However, here's what I know. Just like last time, I know that denominator because the natural log of x is always a positive number anywhere from 8 to infinity, and it's a positive number larger than 1. So whenever you multiply the natural log of x times the x squared, you're going to get a larger number than simply the x squared in this denominator. So if that number is larger than the number in this denominator, then I can say, well, the same numerator divided by a larger denominator makes the fractions in this problem smaller than the fractions in this problem. Now again, what do I already know about 1 over x squared? I know that it converges, and in fact, I already know it converges to 1 over 8. I can tell you what that integral answer is. I don't know what this one is, but I can tell you it has to be less than 1 over 8. I am certain of that. What I'm also certain of is the fact that I'll get some finite answer, it's also convergent. Again, you can just save yourself a lot of thought by just using this rule right here. If the denominator's degree is more than 1 greater than the numerator's degree, it's going to converge. If the denominator is only 1 degree more than the numerator, it will diverge. If the denominator is less than 1 degree more than the numerator, it will diverge. Now, you could try other things if you said, well, I can't do this one by hand. Could I use some software to evaluate this? You could. There's no reason to. I promise you it's going to be a convergent answer less than 1 over 8 because the integral of 1 over x squared from 8 to infinity is going to be your 1 over 8. All right, guys. So hopefully that helps you out with this section. We'll move into chapter 8 after this. We'll look at a couple of sections through there. And then we head into chapter 10, and chapter 10 is just full of logic like we have with these last few problems talking about whenever it's converging and diverging with the values of p, because we get to series and sequences at that point, which is some fun stuff. All right, let me know if you need any help. I'll be glad to.